Well, hello and welcome to Tim Time Projects, where this scary looking thing right here, probably scary because all the leads, it's pretty simple. It's basically going to test a diode to be a switching diode, and what I mean by that is that diode will carry the signal or control where the signal goes. And probably right now would be a good time to stop and take a look at a regular schematic. Alright, hopefully this thing's working. So, what we're going to be looking at is, and don't be horrified by this schematic, it is kind of overbearing, but we're going to be looking at this area right here. I'm hoping that my hand is showing up on here, but it's the filter area. So yeah, that really does look like an intimidating schematic. But if we just zoom into what we want to look at, it's this area right here. And here's some filters. Your transmit receive line comes in here and then goes some way, but apparently it goes back out here, and that's what we're going to look at. Is these are switching diodes right here, and they control what happens or which path this should choose. This is for an option if you have the extra crystals, or the extra crystal filter rather. This would be the option for that. Here's a single sideband filter, and here's the AM filter right here. You can see they tell you voltages here, and by looking at this right here, we can see that 5 volts on the cathode and 0 volts on the anode. Nothing's going to go that way. But going up here, we got 5.6 here. So that's possible. That would work. That's a little bit higher than this direction. So this one's probably turned on. And kind of the same thing over here. It's got 5.5 volts there. And if you look down here, 4.9. So it's running a little bit higher. So they're showing you the voltage drop on the diode, actually, which you can see here. If you follow this, where it says 5.6, and follow this little resistor here, this comes from here. And if you follow this line over here, it goes to a little matrix setup that decides what bands you have on and what you're set. But all you really need to know is when there's voltage applied to this diode and the diode is forward biased, it will start to conduct. And that will let your transmit receive signal go on through. So it's going this way, so we can assume that from the instructions, the setup of this probably at the very beginning tells us that it's maybe 14 megahertz on single sideband. And that's it. So that's how the diode switching works. It's just kind of like a relay where you don't have to send this whole transmit receive signal all the way out to the front panel of the radio to a switch and then back in. You can send a small DC voltage to do your dirty work for you and do the switching. So I'm sitting there staring at this wondering, is that really how it works? And it seemed that was how it worked, but I thought I'm going to take it a step further, and I'm actually going to go and try and build one of these and see if I forward bias a diode, will the signal really ride on it? And can I take that signal back off of it and have a signal with all the same integrity? So that's what this is all about. So stay tuned for a happy Easter version of Tim Time. Alright, sorry about all the shadows here, but I wanted to redraw this to show it more practical how it would actually be if we actually would have been using a filter or something in there. So this would have been our filter, and it would have been fed on the output of that capacitor, because that's where you don't want the DC is inside your filter or your whatever network's following it.
and then the output would go here. This would strictly be the ground circuit. That would be taking the DC voltage to ground. But again, since we didn't have any of that stuff here, we just kind of simulated, and we were testing here, 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 and here. Make more sense? Probably not. Hope I didn't confuse you too much. But here's what we had. So we had the signal coming in, our AC signal comes in here. It can get through this capacitor, goes up to this diode, can't go anywhere past the diode because it's such a small signal. It's below the forward biasing voltage of the diode, which is about 0.7 volts, somewhere in that area. It would depend on the diode you picked. So what we need to do in order to get that to move through there is let's forward bias that diode a little bit. We'll put some DC voltage on it. In my case, I used 5 volts. 5 volts came through here, through these resistors. These resistors were strictly for controlling the voltage and current through this diode. I didn't want to burn it up, so I put these in here. But on your real circuit, they would be chosen to limit the voltage that you were using as whatever your signal voltage might be. You may be multitasking a 12 volt signal or something. So anyhow, once this lifts it up enough to forward bias that diode, well, this AC signal jumps right on that DC and it rides it. Now, so now you have the AC signal raised on the DC signal and it comes through here. So now you've made it through, and that's where we tested here. But you want to do something with it. In this case, we'll simulate going through a filter. So we don't want to put that DC through the filter. We want to strip that back off. So here we stopped here, the DC voltage. So this wouldn't let the DC go through, but it acts as a short for the AC. Sorry, it acts as a short for the AC or for your signal. So the signal flows right through into your filter and then to the output. The DC continues here, and this is the rest of your biasing circuit over here. So you can imagine if you had a series of circuits kind of set like that, and your rotary switch on the front, or your little push button switch, or your CPU, it told which one of these, you might have like 10 of these, it told which one of these 10 to supply the 5 volts to. So your AC signal was waiting on all these lines saying, hey, one of you guys turn on. And the CPU said, turn on this guy, so it turned on this guy. Maybe this is your, I don't know, 3.5 megahertz filter. So it turned on this guy, went through the filter, and then continued on its way. And then when you wanted the 7 megahertz, it turned this guy off and biased when a circuit looks just like this for the 7 megahertz filter. Because your signal coming in, your small signal, can't get through that diode. So it just waits there until something forward biases that diode, and then it'll ride right on that. Once it gets through the other side, well, let's strip that DC back off, kind of like a carrier for AM radio. Just going to strip that DC back off and send the AC signal down the line. All right, hope that was clear as mud for you. Okay, what we have here is this conglomeration of things here. This will be our ground wires. I just have so many leads that I had to use a yellow lead just to kind of jumper them together to keep them out of our way. Otherwise I'd have just way too much. So it's going to have the grounds from the scopes, the ground from the signal generator, the ground from, we're going to use this little scope too. We'll try to give this guy a shot today too. And the ground from my 5 volt power supply. I think that pretty much sums it up. Okay, so what we're going to do is, first thing we're going to do is put a signal in from the function generator, and I'm going to set that. I'll show you where I'm going to set that. I'll set it a very small signal. Maybe we'll pick 1,000 hertz at maybe 1 millivolt, something that'll be below what the forward biasing of this diode is. Alright, so there you can see I have, we'll try 100 millivolts peak to peak. Doesn't much matter, just something that's going to keep it below the forward biasing voltage of the diode. And Now we'll zoom back to the scopes to watch what happens. So what I did here was basically this will be the input. As you can see, the scope and the other scope. I'm using a 10-to-1 probe for the one scope and not for the other. It doesn't much matter at 1,000 hertz. We're not too much worried about that, but just happened to be the leads I had on the scope at the time. And I also have the function generator. So when I turn the generator on, we should start to see a scope signal. So let's verify that. I'm going to turn the generator on here. And as you can see, we now have, hope you're not getting too much glare from the lights. I tried to turn off some of them, but I still needed to be able to see. So I'm going to zoom it in so you're looking more at this little scope here, because then that will give you a view. Let me see if I can tilt it back for it. Are we able to see that? Yeah, we're able to see the scope. All right, let me see. Maybe this angle will cut some of the glare out. All right, so what I'm going to do is I'm going to take our scope. I'm going to move this one actually to get this set of connectors out of our way. All right, I'm going to take the scope. Now I'm going to put it on the other side of the capacitor here. We should see about the same signal. This capacitor is basically acting like a short circuit for AC for 1,000 hertz. Very, very low capacitive reactance or resistance for the AC, but it's blocking the DC. Of course, we haven't put any DC into it yet. So this is on the other side, or the input to the diode, the cathode side. I'm sorry, be the anode side. So I'm going to go over to the cathode side of the diode. And as you can see, we get nothing there. Nothing. So we'll double check if you can watch what I'm doing here at the anode side. Yay! Cathode side, nothing. So I'm moving this out of our way. We don't need that capacitor there for right now. Okay. These resistors in here are just in case my voltages get away. It's just to protect that diode. So now what I'm going to do is I'm going to apply my 5 volts. One side will go to the ground, and the other side is going to go to the input, the input of the diode, the anode side of the diode. So there you go. Now we've got it on the anode side of the diode, and you can see my signal came back. But what I want to display here is you have my signals back, but it's actually riding on the DC voltage. So I'm going to have to turn my scope so the input's not AC, it's DC, and then that way it'll be a direct connect and it won't be filtering out the DC. So let me see, I have to see how I do this now. Let's see, right there. Let's see if I maybe, there we go, DC. Here it is, and I'm going to take away the DC volts. You can see it falls back down. So, just so that didn't confuse you too much, all I'm trying to show you is that I'm putting 5 volts in, and whatever these 2 resistors are dropping, plus the diode itself drops a little bit. But you can see my AC sine wave, and I'm going to start to zoom in with the power. You can see where the AC sine wave is riding. It's the squiggly line. It's riding on top. So let's see, when we drop down the voltage, I think we're losing it. Yeah, so now I have to see if I can get the positioning down. We'll click the auto button and see what happens. You know, there it goes. So the auto, you can see there's an AC signal in there, that's why it's bouncing around. So I'm going to take it back and we're going to go, let me go back to, get out of here, bug. What are we at? 500, or yeah, 500 millivolts. Hopefully you can see this. So what I'm going to do is actually, now if you look here, there's a capacitor. So I'm going to check my signal on the other side of that capacitor, and what that should do is block the DC and just allow the AC. I'm going to tell it to so there it is again. Let's look at our voltage here. Okay, and if you look, you can see we have our sine wave back, and our voltage is 0.06. So we did lose a little bit of voltage on that, but not a lot. What were we at? I'm trying to see what the frequency is, 1,000 hertz. So the main thing to see here is the fact that when I put the DC bias voltage on to turn this diode on, make this diode forward biased, that my signal came through. And you'll see I'm going to take this is the DC voltage, I'm going to take it away, and you'll see that signal goes away. Gone. Put my DC voltage back on to forward bias that diode, and my sine wave rides on the signal. I'll take the sine wave input off. You'll see what I'm talking about. There's the sine wave gone. Sine wave's back on. And there you have it. So I hope that wasn't too confusing, but what I just wanted to prove was that the AC signal coming in, or your weak signal on your transceiver, can actually ride on the DC voltage enough to be controlled by the diode to turn it on, and it decides which diode you turn on, decides which path your weak signal is going to go down, say in a filter board. So let's try one up. So now okay, so I cleaned up the mess a little bit. We're just using this scope. And as you can see, if I don't touch anything, as you can stop. As you can see, my signal comes in, goes through there. Because there's a DC bias, it allows it to get through the diode. Here's my DC bias. Boop. Here comes the signal. It goes through the diode, through this capacitor, which strips the DC component back off of it, and I just have my AC signal back at 1,000 hertz. So let's take another look, a simpler way to do this without building a bias circuit. I'm going to turn this off and get some more leads out of our way, so we're not as cluttered at all. No, we don't have much at all. So I have the input, I have the input going to the capacitor, goes in through here. We're not even going to use these. Those resistors can come out now too. And I'm going to have the output let's see, where would be the most logical place to put the output? Well, we'll leave this one resistor in just to see what happens. But I'm going to have to take this capacitor out, and I'll show you why in a minute. Alright, let's see. What does our signal look like? Okay. Now that capacitor is not going to matter, and that'll all make sense in a minute too. So what I want to do is I'm going to figure out a way to do this. I'm going to add some DC offset to this, which means basically I can make the signal in here ride on a little bit of DC. So let me get my arm out of the way. Offset. Alright, I'm going to start to turn that up. There's 1 volt of offset. Let's see what happened there. 1 volt. How does that feel? That's not getting warm or anything. 1 volt of offset was enough to make that diode start to conduct. So, it just shows you that all you need is a little bit of forward bias to make this turn on, and then your signal can ride on that forward bias almost the same way as your modulation rides on your carrier till it gets to its designation, and then the carrier is stripped away and the modulation is pulled off the signal. Hope that didn't confuse you too much, but that's it. I'll turn the offset back off. The signal goes away. You see I haven't changed the amplitude stays the same. I'm just adding a little bit of DC offset to it. That was a cute little rundown for it was a nice little rundown for this meter, and I hope you were able to see it. I'll zoom you in a little bit so you can see just that meter when. Alright, so there's that. I'll turn the offset back off. Oop, went to 2 volts. So let's see if we can I guess one last thing we could look at without even the offset. If I turn the amplitude of the signal up, we should kind of get somewhat the same results, but you're going to probably see some clipping. So I'll turn up to, there's, I got these weird glasses on, I can't see a thing. 2, 3, 4, 5. Okay, so you can see the signal starting to come up already. I'll put it up at like 1 volt. Okay, that's, these glasses are the worst. That's around 1 volt peak to peak, and you can see it's just enough to turn the diode on. So even if I get to the point where it fully saturates the diode, it'll only turn it on in the positive half. So we've just basically made a halfway rectifier out of it. Let's see what, there it goes. It'll never conduct into the negative half, and that's why the offset would be important, because the offset just makes it sit on top of the DC. Alright, enough confusion. Thanks for watching. I hope you learned something or found something neat or something you can try on your own. Stay tuned for more exciting stuff. Take care.